Okay, can you hear me? All right, so we'll start. It's time to start. And I'm recording this, but I have to say, please tell your colleagues to not miss lectures, because this class is not one where you can miss a lecture without a real reason. So in any case, I say that because I see every time fewer students. So the fact that I make the lectures available is not so you don't come, but is so that you can go back to them and review something. In any case, I'll do my best to remind you. But so today, if I can start a bit with this, I would like you, a lot of students are asking me where to find X, Y, and Z. And of course, I will always tell you, but my emails are never very long because I have so many of them every day. And so they're kind of short. I will try to send you to the right place for information, but I also want to tell you that if you want information about the class, the best place to go is like on the module for the week. And the module, as you see, I have up to date, and then I will ask Friday, of course, depending on how much we do today and what we're going to do. I plan to do problems on Fridays. Every Friday, I will try to do problems and then review the material, because that's the best way to do it. It's very hard to introduce concepts in 50 minutes and then also do an extensive problem, all right? So you need to remember that. Sometimes we can introduce the lecture and the problem, but in any case, so I can go fast. Here, for example, the one thing that you have to do is to check every lecture. There is something that says overview and to-do list. If you go there, I have outlined what you have to do. All right, at least the fundamentals, so you don't forget those. So if you don't know what to do, is that people who are missing lectures and are missing top hat exercises, and they say how to make it up. We have not discussed about makeup in anything in this class, because a makeup activity, makeup assignment, makeup activity is very taxing for me and for every other student, because I will have to create something different. The students have to take it. There are different students who have missed different things. And so it's difficult to make a makeup activity for every individual who has missed something, all right? Consider that we have 150 students between the two sections. All right, so what I plan to do, however, knowing that we are all human beings and we have reasons to miss things, I will have 1 or 2 maximum makeup assignments for this class. One is going to be after the midterm. The other is going to be before the final. By after the midterm, I will know who has missed what for what reason. And then I have a way of creating a makeup assignment that can address different types of needs in terms of points that people missed for a good reason. Don't ask me right now when you miss something immediately, what is the makeup? There's going to be one after the midterm, and I will know how it's going to be. I will explain it to you a few weeks before the midterm, but then I will get a sense of where people stand, all right? And then it's going to be one before the final. Okay, so these two. Having said that, I just terminated the problem you had to do for the exercise on top hat. All right, so now it has been assigned to you as a review. And what I plan to do on Friday is to also go quickly through those solutions for the top hat 2 exercises and then problems. Any questions about those? Okay, so today we are going now here. So you saw yesterday, Monday we did Introduction to Electromagnetic Scalars, Vectors and Tensors, and Vector Properties quickly, because all of this is a review. But today what I would like to do is to go to Vector Operators which is a little more a little more difficult as a concept, because we still want to connect these concepts to physics, to what is happening in nature. There is no point of learning math as a separate, thing from, and then have it decoupled from the physics we try to understand, all right? So we have to bind the two together to be able to make sense, because what I want you to do in the future is to see math and understand physics. If you cannot go beyond that, if you cannot go beyond your math to understand physically what it means that you're doing, you're not going to be able to really handle this class well, or even use its concepts in design later in other topics that you will choose. So now to go to operators, I'm going to, this is where I can write things, all right? That's why I'm here. These are my notes. You will see, these are exactly what I do, two things. I put my notes ahead of time, so you have them available, but then as I add things, if I like what I have, if it's like a nice example, I will keep it, make a new copy of this and put it up again, all right? So if for those of you who feel that you have read my notes before class, make sure you look at them again, just in case I have some new information added to it. So that's another thing. Okay, so operators. Let's, in fact, there is one. What is an operator? When we say mathematically, this is an operator, what do you understand? Let's talk about this first. So a dot product, when we say dot product, is a product between, is the inner product, is not a scalar product, all right? The dot product is a product between two vectors. So at least we understand, we have two vectors, we do the dot product, is like practically as looking at the projection one on the other. You remember when we had two vectors and the dot product was the maximum of one, and the magnitude of one times the magnitude of the other times the cosine of the theta angle that is created between the two vectors. All right, so practically this is like one vector times the projection of the other vector on it. That's one way of thinking it. The other is to see exactly how close the two vectors are. If the two vectors are, the angle is 0, that means that they are totally collinear. So the product of the two is like magnitude of one times magnitude of the other. But if the vectors start deviating like this and then become 90 degrees, then the projection of one on the other is 0. So then the inner product between two vertical, perpendicular, I should say, vectors is 0. Cross product. Cross product is similar in essence to that, but different. First of all, it's not scalar, it has a direction. And second, it shows also the product between two vectors, but also in relation to the sign of the angle. So practically, if two vectors are collinear, the cross product is 0. So what cross, and it has a different direction, all right? So what the cross product shows, it shows how the product of the two vectors projects on different planes, all right? And of course, it's another vector that goes along along another direction. So it's at least we connect that to vectors, and vectors are electric field. When I say vectors, I always think of electric fields. That's what the other thing you should do. We are not in a math class here. When I say vector, the one vector we are going to deal mostly with is an electric field or a magnetic field. So think like that, all right? So two electric fields like that, cross product, it implies is another vector. And it's just the product of the two, but multiplied with a sign. So it shows if they are vertical, so the cross product of these two fields, which is a rotational kind, we will see that, it goes perpendicular to the plane of the two fields and is the maximum. And when they are collinear, the cross product is 0. Okay, so these things, remember that. Now, when you go to vectors, on a vector is an, we'll go to operators. Operator means that we have an entity that acts on another entity. An operator does not need two vectors, does not need two functions that have a direction, all right? An operator acts on one. So there is an operator that we use, one operator, very important, and we call it the Dell operator. The Dell operator, and have you seen this before, the Dell operator? Okay, good. So let me in fact go here. The Dell operator, we show it like that. It's going to be something very useful to us. Is this, is the inverted delta. Delta was the Greek delta, right? That like a triangle. So inverted, and we show it like this. So it's a vector. And the interesting thing that this vector in 3 dimensions, Cartesian coordinates, obviously, because that's the easy one, is practically a combination of all of these derivatives. So now, let me stop at this point, and I will show it like that. So a Dell operator is a vector, but still a vector operator that has, when it operates on a vector, it really gives us a sense of how this vector varies along the different directions, all right? That's what you need to remember. Now, since the Dell operator is an operator, it needs an entity to apply to, all right? By itself, does not mean anything. So it has to operate, that's why we call it an operator, on something before it gets meaning. Now, if the function we have to operate on is scalar, like temperature, so let's consider T to be temperature within a volume. For example, that the volume is defined by Cartesian coordinate system. In that case, the vector, the Dell operator operates on that temperature, and then it creates a new vector. And the new vector is going to be, it's going to have 3 components. And the first component is going to have as a magnitude the derivative of T with respect to X direction. In other words, is going to have as a magnitude the rate of change of temperature along the X direction. And it's going to have another component Y with a magnitude, the rate of change of T along the Y direction. And it's going to have a Z component with the rate of change of T along the Z direction. So if I give you that for one particular problem, let's assume that we solve, we take the temperature in this room, and then we measure that as a scalar function, all right, at every point in this room. Let's assume that we divide this room in many smaller cubes. At the center of each cube, we go and measure the temperature. We have a probe, for example, that goes everywhere, a very thin thermal probe that goes and measures the temperature. Let's assume that you have like a little fiber, and at the end of this, you have a little probe, a little sensor, thermal sensor, goes and measures temperature everywhere. And then we record those data. All right, then we have this data. And then you go from this data, if the cubes are small, and then you take the differentials between the 2 adjacent numbers, and you divide that by the distance, and you get all of these derivatives. All right, you get them, of course, in differential form. All right, so then I plot the function, and I come and tell you that what I found is, if we assume that in our room we had X, Y, and Z. So X is this direction, Y is this direction. So X along the length, Y along the width, and the and Z along the height of the room. Then what if I tell you that the divergence in the gradient, now we call this gradient, in this case, we call that gradient of T. So when the del applies on a scalar, it's called the gradient, okay? Changes its name from del to gradient, the gradient of temperature. If I tell you that the gradient of temperature is x 0.2, what does this mean to you? Let me assume that I did this experiment, and that's what I found. How would you explain the result? What does that mean to you physically? Yes. Exactly. So it means that the temperature is independent of y and z. All right. So it's constant on this plane. So if I go on a plane like this, or like the top wall, all right, and then I go parallel to that wall. Along all of these planes, the temperature is constant, and it changes if my x direction goes from there here, all right, so positive x is like that, it means it starts increasing from the back wall up to here, which is possible the case because I feel very hot up here. So most probably the temperature on this side with all of the electronics and everything is higher than the temperature on that side that has glass and it's connected with the outside. So in any case, that's what it says to you, all right? So try in this class, that's our challenge in this class. If there is any challenge for you in this class, it's not so much that it's so advanced that you have difficulties following it. Is because you will be challenged to think, when you see that, not math, to think physics. Try to do that, all right? And then you're gonna see how much you're gonna enjoy all of the subjects that you read. This is true not for just this class. Classes that have a lot of math, try to go beyond it. Math is a tool. Remember that math is a tool. Keep telling that to yourself, all right? Okay, now, here, of course, you see that, but I explained it to you like this. Why is this here, of course, that's another thing which we are going to do today. Every time in my notes, you're going to see that now, as we will introduce towards the end of this, all of the transformations, because coordinate systems depends on what we want to characterize. This room is a parallelogram. Is so with vertical walls, all right, practically. So it makes sense to use the Cartesian coordinate system. If our room were to be like cylindrical, like assume that the walls were all part of a cylinder, like round, then in that case, how would we characterize that? Using a cylindrical system, okay? If, for example, we were in a dome, all right? So the domes are like half a sphere, practically, a perfect dome. In that case, how you would what kind of coordinate system you would consider to characterize the same kind of temperature variation in a dome? You will use a spherical, okay? But if you had small cubes, rectangular cubes, like, you know, which is like a fundamental shape for a Cartesian coordinate system, and then you would divide the dome in smaller cubes. You can do that. You know, you cannot just approximate, all right, the outer surface. It's going to be a little ripply, but so what? You know, if the cubes are kind of small, you can do this. If you have many small cubes, you can approximate a dome. So in every cube, you can so every cube is going to be X, Y, and Z kind of shape. At the center of this, we measure T, and then we're going to have another cube next to it. But the difference between the T in one cube in the center of one cube at the center of the next cube, you can visualize that, all right? Can only give you a derivative along the x direction. So practically what the difficulty we have is that we can do that division in x, y, and z coordinate system, but then the total thing is spherical. So at some point, after you arithmetically you find the x, y, and z derivatives of the temperature using the adjacent measurements. So what do? Then you use x, y, and z to spherical coordinate transformation to be able then to describe how the temperature varies in a dome, because it's going to vary as a function of the radius. All right. That's why we are forced to have also in mind the need to go from one coordinate system to another. So I give you that as an example. And you will see, as a matter of fact, what it means even to take these operators and apply the operators on functions that have been described in terms of another coordinate system. Okay, so that's, and of course, the simplest is the Cartesian. Of course, we know. As you go to higher, more complex coordinate system like cylindrical and spherical, well, of course, this operator becomes more complex, but we will see examples. All right, in fact, there is an example here that gives you a function. Let's assume that this function practically was nothing else but temperature. I measured it and that's what I found. And I give it to you. And I don't give you all of this data. I give you, I said, I made all of these measurements and I took the measurements and I found by doing interpolations and I was able to approximate the whole temperature with this function. So now for me, find the gradient. So then you will have, if my function that I gave you for temperature is this one, then you'd rather know the gradient in the cylindrical coordinate system to be able to tell me how temperature changes as a function of rho, z, and possibly phi, which is the angle. We will see that later. Okay, so and then of course that's it shows you how to do that. Okay, of course. Then you can also write it in x, y, and z. So you can do a lot of things if you know how to go from one coordinate system to another. It depends on what is the shape of the space in which you have to do something and what kind of coordinates you want to have at the end, because eventually you compute the gradient to do something with it. All right, so that is why we know that. Okay. Now, if you take the same Dell operator, let me add here. All right, before I leave the gradient, tell me, where in real life, because a lot of these things, mathematics, were not in the beginning of times. Mathematics was a construct that we created. But before we developed math, we were doing a lot of things that math eventually was able to write in a very elegant way. It's like, for example, people spoke before they started writing. And that's how humans, all right? We started communicating before there was a written language. As a matter of fact, it's not very old. My mom from Greece comes from an indigenous group in Greece. There was spoke a very old language and it was not written. It was not written. Now, eventually, with my generation, that none of us speaks it. I mean, we understand a few words here and there. It's gone, or it's only on books for people to study. But yeah, up until my generation, there are people who speak languages which are not written. Okay, so it's not a new thing to us that things have existed before we were able to write it down in some ways. Okay, it's the same thing with math. So tell me one of the things that you see every morning on TV. When you turn on TV, maybe in Texas, you don't worry about weather. But in the Midwest, the first thing that people see before they go out of the door
is to see what kind of weather it's gonna be. It's gonna be very cold. Is it snowing? How much has snowed, you know, and all of these things. So what do you see when people show you the news every morning or during the day? What is it, the one thing that you see? What do you guys see? How do they show you the weather? Map. Okay, the map is all, you know, has colors. So what do they use the colors for? So 0, for example, degrees, or like -20 is like a dark blue, okay? And then it goes to lighter and lighter, so it's practically white around 0 or 32. And then it goes a little more pink, whatever they use, and then it goes really hot when it's like what, 90 degrees if there was in the summer. How do they get those maps? Where do they decide to change the color? How do they decide to create those color variations? I mean, on their own, they go like there and they say, oh, here, like North Dakota, today is minus something, put a color there. And then you say, Michigan is there, and then, or Houston is down there. So they don't do that. They take the gradient. The old days, yes, they would do that. The old days, they will put them on the map, all of the temperatures that they will measure, and then they will develop these lines primarily out of a gradient to show the fronts of how the temperature was changing. Because practically, you don't care about the temperature, you care about how it changes to be able to give a very good understanding of how it all plots. So all of these colorful maps that you see, which of course are all scalar maps, all right? But the way that the color has been attributed is not accidental. It's based on how the temperature varies. So the colors follow these lines. Also the same thing you're gonna see. Have you seen mountains that people, a lot of times people who try to measure the height at different levels that draw these lines, all right? These lines come out of this derivative, of this vector that shows exactly how the height of a mountain changes, not how it changes from here to there, but how fast it changes here. If it changes very fast, the line that describes this plane, the height, and that is much closer. And then if it changes much slower, it's much further away. Look at some of these maps, especially when they do a, how do they call it, cartography, all right? When people try to show you a map, but also with the heights of the mountains, they use that divergence, that gradient, excuse me, to be able to map that. So we see it all the time, but now you know how to write it in math. Remember that. So when you take a temperature, which is one of the very important, for example, very important scalar functions we have, or what is another scalar function? Energy, all right, in our field. Energy is a scalar function. But if you have energy stored in a volume and you want to map this, so I can see that you want to map it on a planar map, how are you going to do that? Using the gradient of energy, all right, in whatever space you are. So that's how you need to remember it. Okay, now, from there, we go to this one. And also, I'm going to add a page here. All right, so now when this operator, and I want to make sure that I see the time, when this operator, the Dell operator, applies on a vector, let's assume that I have vector A. How is it going to apply? This is not a, there is no operation like that, all right? Vector times scale, I mean, the scalar product with another vector does not exist. Usually it's like this, of course, all right? So what is this called? This now acquires a different name, and it's called the divergence. And why does it acquire a different name? Because it does in some ways show something similar to the first one, but yet very different. It shows how a vector changes. And sometimes the vector can be not necessarily, can be a color vector, all right? Like we have that when we use colors and you say a vector of colors, it shows how the colors really change in different dimensions. And then that is important, especially if you want to visualize in 3D space. In any case, divergence, therefore, shows now a change of a vector, but what it does is, if you take the inner product and if you know how the divergence is written, which is this, so the divergence is like that, and then we take the inner product of this with a vector who has, assumingly for this example, 3 components, a sub x, a sub y, and a sub z. And then, sorry. And then what do we do? If this is an inner product, then we create the following. We create a scalar now, which is practically the sum of the 3 derivatives. Okay, so that does show the change of the vector, but it shows a composite change of the vector. It does not show how a scalar like temperature changes in each one of the 3 directions. It shows how a vector changes holistically in a composed way, like all of the components have been taking their derivatives along the respective directions, and then you sum them up. So you get a sense of the change of a vector, but without having to show it in the vector form, directly goes into a scalar form, okay? Where are we using this? You have practiced it since you guys and girls were 1 year old or 2, when you started trying to draw on paper. So how do you draw a face if you are a toddler? How did you? I don't remember. I remember my kids, how I still found a place where they were sketching some weird stuff. And usually a toddler, if a toddler sees me, like my granddaughter, and her mom says, you know, do you wanna draw grandma? How do you think she's gonna do it? She's gonna put, most probably, I'll tell you, like this. Probably she's gonna do that because I smile whenever I see her. And maybe she's gonna put something like this. Do you agree? What does this do? Think about that. I mean, I don't look like this. Of course, the distance between my eyes or our eyes, it's not blank, all right? There is a lot of color. Our figures, you know, of course, we are 3-dimensional entities. We have everywhere colors that show the different parts of our face. But obviously, in a very limited way, whatever kids observe may not necessarily observe everything on our face. Their brain may not be able at that early age to process everything. And then they are attracted by our eyes. They are attracted by the shape of our mouth because it implies emotion. This is important to them. They may see ears or not because these are important, but they don't necessarily understand that they hear from here. In that early age, they see hair. All right, that is how they see. That's what their brain remembers. And assuming that their motor skills, you know, are limited, of course. what does the brain try to do? When the brain cannot fill all the blanks, either because it does not have enough information that the brain has maintained, like in toddlers, or because we are in a very fast mode, we want to draw something, all right? Even if we know how a hand looks like, and this is what I'm going to show you here, all right? This is, do you remember, do you know where this is a detail from where? Yes, all right. Michelangelo. This is how he saw the human, the man and the God, I mean, trying to reach, or the man trying to reach to God somehow. This is where my guess is he was a great painter. He had people that he could study a hand before he would draw it, obviously like that. He knew how hands look like. All right. Never a painter of that scale goes immediately to paint that. They go through a series of drawings. These are real drawings from him. That's how he was studying how to do the hand. But do you think that he was painting the whole hand? No, only what? Only the places where light had a distinct change in the color. All right, so if, for example, your function is color, and then you characterize that as a function, all right, to cover all of the colors, and then you see a distinct change between my hand or my hand that has this maroon color, all right, because I'm wearing my dress, and then the back of the wall that is totally white. How are you going to draw my hand if you don't want to spend too much time on it? You're going to do only the outline. What does the outline mean? It's the only place where the color changes drastically. So practically what you see is that if color is a function, then the outlines and the drawings are practically the divergence of this function, which is a vector because color changes in all three directions. We do that, all right? We just later found a way to describe it mathematically. So think of that. When I say the divergence of a field, I mean how it changes fast. That's what I care about. That's why I'm going to find the divergence of a field. And then now I'll give you another example. Here, I was thinking about that because, you know, the most difficult thing is to give you examples that you remember from real life so you can connect to the new math. Another example, how will a kid, always, I like that, would draw the sun? How would you guys draw sun, or girls, when you were in, were doing some, would you, I was doing, even now, I draw a sun like this. Let me see. Okay. So what if the sun becomes very small? This is in fact the sun how we see it. But if the sun is a star far away and you want to do stars on the sky, how do you do the stars? Don't you do it like that? And maybe you can do it like if it's like this, because the stars are not like total round. I mean, because of light, they have these kinds of like rays kind of thing. So they are like twinkling something, all right? So what does that mean in terms of energy? Think that energy, or like the electric field, think about that, is in the case for the sun and those stars is radiation, all right? So it's radiation. Let's assume that radiation is a vector, in fact, because it is a field, all right? It comes in different directions. It has different values. And along any three of the coordinates of any system, like in the case of the sun, for example, you will use the spherical coordinate system, all right? Assume that is all the sun alone and everything, the whole space around it. So you see what happens? We see it like a dot. And then we see the rays coming out of it. The rays are not necessarily, it's like how our eyes see, but in reality, they are small explosions that happen on the surface of the sun, all right? And that's how, okay. What we are gonna see is that this gives us, that picture is the divergence practically of a vector that shows that is showing the radiation as a vector coming from the sun. So the electric field, for example, assuming that the sun is a whole set of charges, practically what that shows, this simplistic example here, or here, it shows exactly where the charge is located. And practically, that's what the divergence of an electric field shows. All right, the divergence of the electric field, practically, the way especially we're gonna work with it, if you integrate the divergence of an electric field around a closed volume, if there are charges in there, then you're gonna see a non-zero number. If you integrate the divergence of the field anywhere else, you're gonna see zero. So if I were to go and plot that, I would see exactly this kind of picture that I show you here. I will see on every star that radiates a non-zero value, which means that there is charge in there, and everywhere else in between zero. So wherever there are sources that create electromagnetic radiation, the divergence of the electric field is going to show us those sources. So practically, without knowing, we draw these pictures. You know why? Because our brain does those functions inherently. Our brain has so many sensors to work with: eyes, all right, ears, touch, smell. I mean, things that, and especially the eyes is the one that occupies like 70% of the brain for optical. What does the brain do? You know what it happens with the eyes? In the eyes, like is like an antenna, right? Assume like the eye was like they had 1 billion little antennas in there. So each of these pixels, you know, is a photo detector practically, and takes light that comes. And then the eye, the retina, is processing. So it's doing a lot of these things. What the retina is trying to do, I mean, over evolution, of course, is trying to integrate, integrate noise out, look at derivatives, integrate the derivatives to see where the sources are. And that's why we see a sun like this, like a little kid sees that, because the brain, that's what the brain perceives. That's why we see the stars like that, because that's what the brain perceives. So we have already been working like this, but now we have the math. And I want to remind you that this math that you see is something that we inherently doing without knowing it. All right. So the curl operator is now, what is this operator? It's still Dell. Okay, add page. It's a Dell operator, but now it applies on a vector, but not with the dot product, with the cross product. And let's assume that it applies on this vector A. Now, what is the difference between the divergence, which is a scalar, and what is the difference between the curl, which is a vector? The divergence shows the location of sources, all right? So the divergence of a vector, if there is a finitesimal source, right on the source is going to be non-zero, and at any other point around the source is going to be zero. Especially you see that when you integrate, I mean, because it's difficult to work with infinitesimally small, all right, entities like it is a derivative of some sort. But the curl is a vector, it's not a tensor. And it still shows change because, you know, practically how is this done? Theta x plus y, theta y plus z, theta z, cross product. Let me erase that. And the cross product is with x, ax. Do you remember how to do cross products? The way I do them, and may not be exactly like yours, but this is how I learned it when I was very young, and it's very difficult to forget. So I'll tell you how I do that. I take this, and I have theta x, theta y, theta z, and then of course x, y, and z here. Let me move this down a little bit. This down and up. Okay. And then I have here ax, ay, az. And the way I do this is I take this, all right, or practically I take this and then this one. So I put x and then I take theta az, theta y minus theta ay, theta z, theta ay, theta z. And then when I go to the second one, I put a negative here, minus y. And then practically, I will do this. And then I see the rest, which is like a square, and I do theta az, theta x minus theta ax, theta z. And then I go and take z with a plus sign. And then I do this here. And then whatever is left, I do theta ay, theta x minus theta ax, theta y. All right. So practically the curl is more complex, but what it really shows is where it's useful. When the field is rotational, when the field has a directions like when the water goes through the sink, if you fill up the tub and you see how the water goes, probably in fluid mechanics, if you guys had any of this, you will see that. You will study how the water goes down, all right? It has this, takes this rotational, and then it gets fast as it goes down there, obviously. But in cases where the electric fields have this rotational, and usually it happens when the sources satisfy specific conditions. When they are rotational, that is the curl of A is what it shows how strong this rotation is. All right, so remember that curl shows rotation, divergence shows change for a vector field, gradient shows change for a scalar field. All right, and that's how we are going to use them. Okay, now, I think I'm having only 1 minute, but here are, please see all of these in the various systems. I have those extensively, and then we'll talk next time when we solve problems, all right? Next time we're gonna solve problems on the things that we cover Monday and today. And then we're gonna talk about how we classify the electric fields. I'll give you different examples of electric fields, and we're gonna find, or of other scalar, we'll find the gradient, we'll find the divergence, we'll find the curl, and then we are gonna see what that looks really, what it tells us for electric fields specifically, all right, in some problems. But study. So when I go back here, okay, so please study. This is still review when it comes to coordinate systems.
I give you here all of the information about coordinate systems and how you change from one to another. I give you everything, but please, it's just a review, so we group it together. All of these things are in part 1 of the book. Okay, part 1 of the book is very extensive, which is pages 1 to 108, but it shows everything that you need to know with examples. You will have to just glance at those and use them as you need. This is everything you have to go back to. And then, so we are starting with electrostatics. We talk about Coulomb's law, but we are going to solve problems of electric fields, electrostatic fields, all right, using all of this math that we introduced. And I will remind you what it means every time we use an operator, all right, or every time we do some kind of operation between an electric field and another electric field. We'll always try to remember physics behind that, not stop at the math. Okay? Any questions? All right, so one more thing. On Zoom, I will start a new, oh, not Zoom, sorry. What did I say? Zoom. I meant not Zoom, of course. Okay, I'm starting a new exercise which has to do with coordinate systems. I'm giving you some vectors and I'm asking you to change them. The question is the following. What does it say? I'm giving you the vector in the cylindrical coordinate system, and I'm giving you 4 possibilities of how that may look in the X, Y, and Z. All right, so practically before you solve that, just do a transformation of the vector I gave you from the cylindrical to Cartesian and then solve this problem. And then you will have that until Friday morning before the class. All right, so I will assign it now. Any questions? Okay, we're good. So office hours today. I will only have 1 hour office hours today from 4 to 5 because I have a Zoom meeting for research before and one for after that I had to participate. Okay.